So this next little section is on different types of relative mass. Now, relative mass is actually something you've looked at before, you might not realise it. When we're talking about relative mass, what we mean is working out how heavy something is. So that's something you've done before whenever you're working out the mass of an element. You look up the mass number. And also if you're doing like a mole calculation and you want to work out the mass of a compound, you would add up all the mass numbers for all the elements in that compound. So what we're technically doing there is working out relative masses. One thing we need to sort out, a wee kind of misunderstanding or uncertainty you might have from GCSE, is that sometimes we use different terminology or different terms to describe relative mass. What I mean by that is you might well have seen relative mass described as like RFM or MR, you might have seen it, or like RAM or AR or even like RMM. So like there's lots of different ways to describe masses. What we need to clear up is some of these terms are used for specific types of masses. That sounds a bit scary. What I mean more is like they're used for specific types of chemicals. So for example, some are used for atoms, some are used for compounds, some are used for isotopes, things like that. So in this section, I'm going to clear up what we mean by different types of relative mass. So you'll see in the notes there's 4 categories here we need to work through. And the first one is the relative atomic mass, which is called RAM, or if you want, you can call it AR, the big A with a small subscript R. The definition, and this is a definition that could come up in the exam, is that it's the average mass of an atom of an element relative to 1/12 of the mass of an atom of carbon-12. So there's a lot in that, obviously. First thing to touch on is the idea that this is the atomic mass and it's for atoms. So that matches up in the definition. So we're not using this for compounds, we're not using this for molecules, it's for one specific atom of an element. The next part of the definition you did cover GCSE, but probably was skimmed over. It says it's the element relative to 1/12 of the mass of an atom of carbon-12, which sounds horrendous as a sentence. The reason we got that there is that obviously with atoms being really, really small, we can't use their mass in terms of grams or kilograms because that'll be a tiny number, be too hard to use. So we use their masses compared to each other. So we take a heavy atom and a light atom and we compare the two masses together. For that to work, you need to have like a reference atom to compare everything to. And the reference atom they pick is carbon-12. So it's the reference number. And we decided to make it relative to 1/12 of the mass of carbon-12. So in other words, that gives carbon a mass of 12 exactly, which you want it to. Hydrogen is 1/12 of that mass, so it gets a mass of 1, etc. You might wonder why don't we pick the lightest one, because it would make more sense if we just said is compared to hydrogen, which is a mass of 1. The reason is that carbon is the kind of the best reference. It's quite stable, it's quite abundant, it's really easy to work out an accurate mass for it. So that's the one they settled on. You don't need to worry too much about that, that's not going to be too in-depth. As long as you know that when you're talking about relative masses, you mean it's relative to 1/12 of the mass of an atom of carbon-12, and you can quote that. So, that's described in the next paragraph. I'll skip over. So the RAM is an average mass, so there's different isotopes of elements, then a weighted average must be calculated. So if you want the mass of carbon, you need to take into account all the different types of carbon you've got in a sample, same with any element. And we use this equation here to work out these relative masses. This is something you should have seen in GCSE. Mass of the first isotope times by its abundance, plus mass of the second isotope times by abundance, plus etc, etc. If you've got any more isotopes, divided by the total abundance. So abundances are normally given as percentages, which would make the total percentage 100. So the classic example you looked at in GCSE was for chlorine, So to calculate the relative atomic mass of chlorine, 75% are chlorine 35, 25% are chlorine 37. So mass of the first one, 35, times by its abundance, 75%, plus mass of the second one, 37, times by its abundance, 25, divided by the total, which is 100. Type that in your calculator, you come out with a mass of 35.5. So that's all kind of normal in GCSE. They can make it a wee bit tricky for you at A level, not in terms of making a different calculation, but just kind of presenting the information a little bit differently. So in this question below, we're told about boron. It's got 2 isotopes. One has an isotopic mass of 10, one has one of 11. There are 4 times as many heavier atoms as lighter ones. So what's the relative atomic mass of boron? If you think you're ready to do it, just do it now. Pause the video and have a go, and you'll see what the answer is in a second. If you're a bit confused with that, I'm going to talk you through it now. There's actually 2 ways to kind of approach this one. I'm going to show you both. So looking at the question, we've clearly got 2 types of boron boron mass number 12, boron mass number 11. The question said that there's 4 times as many heavier ones as light ones. So if I had 1 boron 10, I would have 4 times as much. I would have 4 boron 11s because that's the heavier one. That's actually enough to work out the relative atomic mass of boron because it doesn't need to be in the percentages. All I need is the mass of the first isotope, which is 10, multiplied by its abundance, its relative abundance is 1 in this case, plus the mass of the second one, which is 11, multiplied by its abundance, which in this case is 4, because 4 times as much as the other one. And then a little twist here, instead of dividing by 100, which would be for percentages, I just divide by the total abundance, which would be 1 plus 4, which is 5. And if I type that in my calculator, I actually get the correct answer, which is 10.8. Now, you might not like that, you might not like it, the fact that it's not percentages. You can actually do it in a percentage way as well. So if I write out again what I had before, it's boron 10, boron 11, it's a 1:4 ratio. What I can do is try to turn that into percentage ratio to make it out of 100. So at the minute that ratio is kind of out of 5. So I've got 5 boron atoms, 1's 10 and 4 are 11. If I multiply it up to make it out of 100, that'll make life a lot easier for me. So what I'll do is I'll times it by 20, both sides, and that should get me 20 to 80 ratio. So still the same ratio, just multiplied up, and now it's out of 100. So essentially that means it's 20% boron at 10 and 80% boron 11. So I can do the sum as before, 10 times 20 plus 11 times 80 over 100, because it's 9% out of 100, and that'll get me the same answer. So you're very used to the idea that you see percentage in these calculations. Just bear in mind, it doesn't have to be percentages. It's just relative abundances divided by the total abundance. But if you like percentages, generally you will always be able to convert them into percentages, if that makes sense. So that's the first one. Relative atomic mass is for atoms. Next one's a bit more specific than that. Relative isotopic mass. So the mass of an atom of an isotope of an element relative to 1/12 of the mass of an atom of carbon-12. So the end of the definition is still the same, that's not changed. It's just what the definition is referring to is different. Instead of the mass of an atom, just in general, we're looking at a specific mass of an isotope of an atom of an element. So that maybe seems a wee bit kind of unusual. It's easier if we see in comparison. If I was looking at relative atomic mass, that would be, for example, chlorine. So if I look up the mass, the average mass of a chlorine atom in the periodic table will come out with 35.5 according to the calculation we just did. If I was talking about the relative isotopic mass, I would have to specify one specific element of chlorine, maybe the 35 one, could be the 37 one, doesn't really matter, but I'm specifying one. Notice I didn't do that here, I just said chlorine in general, which gave me the average mass. The relative isotopic mass of that chlorine isotope is just its mass number, so 35. So what I mean is, relative isotopic mass is a little bit more specific than relative atomic mass. They're both talking about like an element, but with relative atomic mass, it's about the average of all of them. Relative isotopic mass is the mass of one specific isotope, even if there's a range of them you could pick from. So if you want to be nice and specific, using relative isotopic mass. Okay, so that's the one for our atoms. The next two, or the last two, are about compounds. So you've got two types of relative masses to describe compounds. First one is the relative molecular mass, the RMM. You would use the relative molecular mass for this. It's the average mass of a molecule relative to 1/12 of the mass of an atom of carbon-12. So it's for compounds, obviously, so I could use the relative molecular mass for things like CO2, H2O. So for example, CO2 is going to be 12 plus 16 times 2, which is a mass of 44. For H2O, it's 2 times 1 for hydrogen plus 16 for oxygen, which gives me a mass of 18. So it's just like we did in mole calculations before, add up all the mass numbers to get the relative molecular mass. The one thing that's important to bear in mind is this is only for molecular covalent molecules. In other words, things that have simple molecular structures. You might think that's very strange and specific. The reason why we're kind of specifying that is when you're looking at one molecule of something, that's one individual kind of unique unit. So CO2 is like one individual thing. I could pick it up by hand if it was big enough and could separate it from everything else. So it's one specific thing, so I can say what the mass of that is. Easier to see why that makes sense in terms of comparing it to the last one, which is relative formula mass. If I compare to like NaCl, so say I wanted to work out the mass of it, I can't use the relative molecular mass to describe that because think back to GCSE, NaCl, metal, non-metal bonded together, that's an ionic compound. And you think about the structure, that makes an ionic lattice. So if I'm talking about salt, which is sodium chloride, I'm not talking about like one individual NaCl I can just pick up with my hand and move about. It's a giant lattice where all the Na pluses and Cl minuses are all joined together. It's not like one discrete individual unit like molecules are. So for that, I have to use what's called the relative formula mass, where I just say, look, let's just imagine that's one individual thing. I'm going to add up the mass of the formula. So I'd use that for ionic compounds. So in this case, it'd be 23 for sodium, 35.5 for chlorine, which makes 58.5 as the relative formula mass. Definition-wise, just about relative formula mass, the mass of a species relative to 1/12 of the mass of an atom of carbon-12. So it's a bit more general, it's just a species that isn't necessarily a molecule. Maybe it gets a little bit more confusing. I said we'd normally use it for ionic compounds because we're not allowed to use relative molecular mass for ionic compounds because they're not molecules. Though technically speaking, this is the most general, so you could use relative formula mass for covalent ones as well, and that's probably what you did see at GCSE, because whilst CO2 is a molecule, it's also still a formula, so you can just treat it as a formula and add up its mass. So it's easy to get a bit bogged down by that. Let's just do that one more time. These are the two relative masses to describe compounds. Two options, molecular mass and formula mass. Molecular mass is only for simple molecular covalent molecules. So things like CO2, H2O, it's all non-metals, they're all individual molecules. The reason we can say it's a molecule is because it's like one discrete unit. It's not like part of a big lattice. So if I'm talking about CO2, that's one individual thing I could add up the mass for. The contrast is relative formula mass. That's for generally things like ionic compounds. The reason I can't use molecular mass for this is because that's not a molecule. It looks like a molecule, it looks like one Na and one Cl, but we know from our understanding of structures, from GCSE, it's a giant ionic lattice. It means there's millions of Nas, millions of Cls in a giant grid. So I'm kind of pretending it's one individual thing when I work out its mass, 58.5, by adding up Na and Cl. That's actually the relative formula mass. So to see if that makes sense, I'm going to do a wee exercise with you just very quickly. I'm going to give you some things to categorise. So what I mean by that is I'm going to give you some formula. So H2 MgCO3, CO2 Mg13C, let's go for B, and CaO. So here's some formula. What you could guess at an exam is work out the relative masses. Now that's not what I'm going to get you to do here because that's easy. That's just adding up their mass numbers in the periodic table. What I want you to do is to categorise using the four options we've got, RAM, RIM, RMM and RFM. I want you to work out which one is the most appropriate definition to use. So do the first one example, for example H2, that's not actually an individual atom of an element, that's a diatomic molecule. So I can't use RAM because it's two hydrogens joined together. Can't use RIM because I'm specified an isotope. This is actually a molecule of hydrogen, so I'd use RMM. So that's kind of what I mean here. Just want you to categorise what definition is most appropriate. So pause the video if you can, have a wee go, see if you can sort of figure out in your head what the correct ones are, and I'll go through in a second what the answers are. So MgCO3, that's a metal joined to some non-metals, that's an ionic compound, therefore it's not a molecule, it's just like a big lattice, therefore I use RFM. CO2 is an example from the notes, it's an individual molecule just by itself, so I'm allowed to use RMM. Mg is just an element by itself, so it's not a compound. I haven't specified what isotope of magnesium it is, therefore it's probably going to be an average of all of them, so it's RAM. With this carbon, I have specified one specific isotope, which means I should use RIM, the isotopic mass. Boron, same as before, that's just like an element in general, so use RAM. And CaO, that's a metal joined to a non-metal, therefore it's an ionic compound, it's a giant lattice, it's not a molecule, therefore it's the RFM.